Welcome to Physics 2211, Lab 3, Black Holes by Blake Schwabi. Introduction. The purpose of this lab is to explore black holes and the gravitational forces acting between objects in the system. Principles used within this is Newton's second law, force equals mass times acceleration. Newton's third law, reaction force is equal opposite reaction force. Gravitational force, G m1 m2 over r squared, G being universal constant for m1 and m2 being the mass of the objects that are having the gravitational force, and r squared being the distance squared from one center of the object to the other. And then the net force that we have is just all the forces acting onto the object added together. And using the coding information that we have, when given enough information, we can figure out how to graph certain objects or systems to gain useful information about the system and how the forces work on them. This is the code for part 1, finding the mass of the black hole. So what I did was I changed in delta t to 1 day in seconds, which is 86,400. I then calculated changes in velocities, momentums, and the net forces using their respective formulas. I then gave star.m the correct mass, and then calculated the black hole's mass with the average mass as the force changes over time using the position to get the most accurate answer. And also I did subtract 1 from the total count because it accidentally added 1 throughout. And this is the model that I got for part 1. It gives the most accurate data for the forces and the mass. The arrows point in the correct directions when fully done. I could not put a video on this as it kept glitching out, but you can look at the code in the description. The mass that I got from this is 1.69903 e to the 34 kilograms. Now the code for part 2, not crashing into them. So what I did was I added the mass from part 1 into part 2 in the bh.m. I then added speeds to make the graph most accurate. That is known as in ship underscore speed underscore x and y respectively. And then I used the gravitational force formula to get the forces to accurately graph the motion of the ship and the planet. You can see this on all F's, blank object 1 on object 2. That would be where you would find them. Now here's the model for part 2, with the ship being the purple line and the planet being the blue line. The ship is the closest line I could get to the black hole without crashing into it or the planet. The velocity in the x direction that I got was -6 e to the 7 meters per second. The velocity in the y direction is 1.95 e to the 6 meters per second. Both of them are less than the speed of light, so both are valid. So this is a very quick discussion of it. Velocity I showed you was -6 e to the 7th meters per second. Velocity in the y direction was 1.95 e to the 6 meters per second. Mass being 1.69903 e to the power 34 kilograms. But some of these have a bit of errors within them. With the coding system itself, I could have made a personal error writing into it. The code could have a slight error in it, or there could be rounding errors that can make the evaluations not as precise. But here's the conclusion. What does it mean? Well, there are two separate things on there. Net force and the rate of change of momentum. These are different, as in net force is the total amount of force acting on an object from one or multiple different sources added together, while the rate of change of momentum is directly related to the force applied to the object over that period of time. Now, what if? If, instead of not crashing into it or just getting as close as possible without to, what if you wanted to orbit the black hole? What would you need to do? Your momentum would have to be equal to the force that is acting on you by the black hole to achieve a stable orbit around the black hole. After hours of trying this, I could not find a very accurate model to represent this in my system that I found. Now this would be leading to human error. And with all that, thank you for watching. Hope you enjoyed.